Okay, we're back, and this time we're doing some mechanics. This is kind of a classic mechanics problem, which, as far as I know, every mechanics course in history has tried at some point. In my day, it was called the bug on a bowling ball, okay, bug on a frictionless bowling ball, to be more specific. And I know in our textbook, more modern textbooks, they do this as a skier on a large frictionless spherical snowball. It's kind of a weird problem. You don't see this every day, obviously, but a lot of good mechanics, a lot of good physics here. And it's a nice combination of two key ideas, which is going to be the conservation of energy and some circular motion, since you're on a sphere. So here's the general picture of what we're talking about. I'm sure you admire that little drawing of the bug up there. So the idea is the bug is going to start to slip down the ball, and at some point it's going to leave the surface at a particular point. And our job is to try to figure out what's that angle it's going to slide down before it leaves the surface of the ball. Okay, so that's the problem. Okay, well, a couple things here. First, we know that we're going to be on a circular path, part of a circle. Anytime we have that, it kind of screams out we're going to have centripetal force. So we know the radius of the circle, it's just the radius of the ball. The bug has some mass. We have to figure out the speed. But then we also want to consider what's the force diagram when the bug gets down here to that special point. Well, obviously there's going to be gravity. And because there's no friction, we don't have any tangential forces, but we do have a normal force. Okay, now centripetal force is anything that points along the line of the radius, okay, going to the center of the circle. Well, the center of the circle is the center of the ball, and the only inward force we have is that kind of like inward push that gravity gives you. Now, according to our picture here, this would also be the theta of our drawing, and so that component of gravity is just like being on a hill, and it's mg cosine theta. Notice, though, we also have the normal force, which is a radial force, and that points away from the center, so we have to subtract that. Okay, so as the bug is sliding down, this is your centripetal force equation. It's not as simple as it might look because your angle is changing, which means that your speed is also changing. And our job is to find the speed when you're right at that point that you leave the surface. Now that's also the key. When you leave the surface, think about how strong is your normal force? How strong is that pressure between the bug and the ball? Well, if you're just about to leave the surface, your normal force is approaching zero. Okay, so that's the condition that we have as far as the centripetal equation. Our job is to solve for theta, so the other unknown that we have is speed. Well, my rule of thumb is if you have to find speed, think energy. And here's a case where your initial energy is when the bug's at the top of the ball. And so it's all potential. The bug's starting at rest before it starts to slide. Now, what height are we talking about? On our picture, the change in potential energy that gives us the kinetic energy, well, it falls through this height right there. Okay, it's not the entire radius. That's what a lot of students tend to miss. So our job is to figure out what's that height. Well, fortunately, we have a little triangle here. Okay, so this part of the triangle, and here the hypotenuse of our triangle is the radius of the ball. Well, this is going to be r cosine theta. The total length over here, the height that you're starting off relative to the center, well, that's the radius. So the height is going to be the radius minus the radius cosine theta. That's that difference that we want. Okay, so our energy equation is the potential energy is mg times this height. And by the time you get to the point where the bug's leaving, it's moved through that height, and so all that gets converted into kinetic energy. The mass of the bug drops out. Okay? So now I can go ahead and we can just solve for v squared. That's what we need in our centripetal equation. So velocity squared is going to be, that factor of 2 comes up, 2 times gravity times the radius, 1 minus cosine theta. Let's put that back into the centripetal equation. Now we have mass times v squared. Well, 2gr, 1 minus cosine theta. All of that's over the radius. And that's all equal to mg cosine of the angle. Well, radius drops out, mass drops out once again, even the acceleration of gravity drops out. Now let's figure out cosine. Okay, so on the left-hand side, what we're left with? We're left with 2 minus 2 times cosine. That's equal to cosine of the angle. Or 2 is equal to 3 times the cosine of the angle. And now we have our answer. Cosine theta is 2/3. Or if you were to punch it into a calculator, it's somewhere in the neighborhood of, I think it's 48 degrees, 48.1 or something like that degrees. Now this result, the interesting thing about this is not that it's 48 degrees, and it's kind of a strange angle, seems arbitrary, but that turns out to be correct. This angle, it's independent of the radius. Okay, it doesn't matter how big your ball is. It's independent of the mass. Okay, it doesn't matter how big or heavy your object is that's sliding down this frictionless ball. That's why this works for all cases. It works for a bug on a frictionless bowling ball. It works for a skier on a frictionless large snowball. Okay, or any other variation on a theme that you can dream up. It's always going to give you the same answer here. So again, it's kind of a neat little example of how some different mechanics topics are combined. We had centripetal force, we had force diagrams, we've got some energy going on, and in the end we found out our answer. Okay, so I hope this helps. Hope you found it a little bit interesting, and until next time, we'll see you later.